And welcome once again, AP Physics, to the Simpkins Physics Corner, bringing to you live friction today. You know what really grinds my gears? Friction. Yeah, it does. Don't tell friction jokes. I won't let them slide. Oh, it's terrible. But we're going to jump into friction today. What is it? How do we calculate it? Where does it show up on our equation sheet? And what does all this crazy stuff mean? So the cool thing about this unit is that for dynamics, we only get really two new equations on our equation sheet. All right, there's F equals ma, which is really this right here. And then we also get this force of friction equation, which looks nuts. All right, so first of all, what is friction? Well, friction always opposes motion, as we've said before. So three quick examples I always like to give. If I have a box sitting on the ground and I push on it and it doesn't move, why does it not move? Because I'm not pushing hard enough, because friction is pushing back on me. So friction could oppose motion in that sense, is that if I push something, it's not going to move until I push harder than friction does. Another example of opposing motion, if I put a block on a ramp and it doesn't slide down the ramp, why not? Because friction is opposing motion. The friction would be acting up the ramp, preventing the downward motion from taking place until either the ramp was slippery or the ramp was too steep so that friction can't hold it anymore. And of course, the last example is if something is actually actively moving to the right, it has a velocity to the right. If something is actually moving to the right and friction would be slowing me down, you can see how friction opposes motion. So I really like that phrase to kind of capture what friction is. Of course, it's measured in newtons, and there's two types of friction. I want to talk a little bit to you today. I've had you guys assigned you the College Board video for contact forces for friction, and in that video, they do an experiment where they pull a block, and they pull harder on this block sitting at rest on a table until it just barely starts to move. And that's what all this absolute value less than or equal to nonsense comes from. All right, and this actually makes a lot of sense if you think about it. So let's go ahead and consider that video. That would be the College Board one. In the video, they had a block and they increased the force on this block. Steady. So first they had zero force, and then they increased the force. They pulled harder. Now, when something is not moving, all right, the table surface and the block are not moving relative to one another, that's called static friction. And the way I help students remember this is static, stuck, sticky, stronger, still. Static friction is a stronger type of friction generally, all right, in the sense that we get a larger force from it. And the coefficient of static friction, this little mu thing, if you're the Pokemasters out there, you know that mu is a Pokemon, but it's also a Greek symbol for the coefficient of friction, which just means a number for friction, all right? So something like 0.5 might be an example of the coefficient of static friction. Now you'll notice the friction gets larger and larger the harder and harder we pull. So this is the first thing a lot of people mess up. They think friction is like some steady force. Well, no, if I pull just a little bit, friction will just pull back a little bit in reaction. Newton's third law. If I pull a little harder, Newton's third law says that the force of friction will pull back a little harder. But eventually that friction can't hang on anymore. And that's where this thing comes from, all right? Think about this. The force of friction is less than or equal to. What that means is the force of friction is going to build, all right? And then finally, eventually, if I pull hard enough, friction will be less than, all right, or it might be equal to. And that's kind of a strange thing to think about, but as we see some problems today, I hope that this will become a little bit clearer for you. So what happens then? You pull, finally the friction gives way, if you will, or there's not enough friction to keep the block from moving anymore. Well, now that block is moving relative to the surface, and anytime we have two surfaces moving relative towards each other, we call that kinetic friction, like sliding friction, kind of, right? And so the way friction works is no surface is actually smooth. Imagine the surface of the table to look like this with all these mountains and valleys, and imagine if we zoomed in on the surface of the block, it would look like this with all these mountains and valleys. As they are at rest, those mountains and valleys kind of settle into each other, and that's why it's kind of hard. I say it's stronger to overcome the static friction. I say it's harder to starter, because as you pull on it, those mountains and valleys are kind of interlocking. But once you get that block up and over on that microscopic level, once you get it up and over those mountains and valleys, now we're kind of skimming across one another, right? There's not time to settle into the next mountain valley combination there. They just kind of slide over the top of each other, and there's less resistance. What we call that is kinetic friction. So there's two types of friction, static and kinetic. Static, stuck, sticky, stronger, still is when two things are not moving relative to each other, and kinetic friction is when two surfaces are moving relative to each other. And so that's for you right there. Let's look at a couple of examples. Mr. Ames is dragging a box full of books. The box has a combined, wait. All right, so we know that's the force of gravity of 134 newtons. If the coefficient of static friction between the pavement and the box is 0.55, there it is. That coefficient just means a number. Don't confuse that with the force of friction. We're talking about the coefficient of friction. How hard must Mr. Ames push horizontally in order to start the box moving? So he's going to give us an applied force, and we're going to have a backwards force of friction here. And of course, the ground will be pushing up with some normal force. Okay, now, on any flat surface, the gravitational force down and the normal force up, if there's no other vertical forces to contend with here, those have to be balanced, right? Because we are not accelerating up or down, therefore we must be in up or down vertical equilibrium, so the normal force and the gravitational force are equal in this case. All right, let's continue. How hard must he push? Well, we know that in order to get this thing moving, he has to push at least as hard as the force of friction. Okay, so his applied force has to be at least as big as the force of friction. Well, we know that the force of friction is going to be represented by this mu Fn. Now you may say, Mr. Simpkins, hold the phone. What happened to all these, less than or equal to and all that stuff? Well, think about this. We're building into this idea of the problem. I'm going to pull harder, harder, harder until finally it breaks. Okay, that basically we just set the friction moment to maximum, right? So we set it at its highest value because we need to pull until that friction gives out or gives way. All right, so I'll come back to this here in a second when we have our answer. So all we have to do here for that is just say 0.55 for our coefficient of friction. Our normal force is 134 newtons. And then if I drop that into my calculator, I can get my applied force for the force of friction. Now, the answer here is going to be 73.7 newtons. Now, that is how hard he has to push to get it moving. So let's revisit this idea of the craziness of FF is crazy equal less than or equal to mu absolute value, all this nonsense. All right, let's consider that. Well, think about it. If Mr. Ames pulled with 60 newtons, right, then force of friction would be equal to 60 newtons. It wouldn't be equal to the 73.7. That's where that less than or equal to comes from, right? So again, the force of friction will continue to react by Newton's third law to the amount of force it's resisting, and then eventually, if it doesn't have the capacity to do that anymore, that's our maximum value. And so our answer for this problem is 73.7. Let's look at another one. You push a wooden box across the floor at a constant speed. All right, so constant speed means balanced forces. All right, that's one of our conditions for equilibrium. So if we have Fg down, Fn up, we have Fa, our applied force, and we have Ff. Since we are going at a constant speed, we can say for certain that Fa is equal to Ff. Well, just like our last one, let's see. So we're pushing it, and it says the coefficient is 0.20. So if I do mu times Fn here, that would be 0.20 would go there. But what about Fn? Well, I get kilograms. So let's remember what kilograms is telling us. Kilograms is telling us about mass. And we can get the weight, force of gravity, we can get the weight from the mass by using F equals ma. Because really, Fg is equal to mg. Those are kind of both the same equation. It's just that g is a particular value for the gravitational acceleration. So I can find a weight, or force of gravity by simply doing the mass times 9.8. Remember, we round g to 10 anytime we're doing a multiple choice type problem, just like the College Board does. But when we actually do problem solving like this, we'll go ahead and stick with the 9.8 for all of you precise physicists out there. Now, if the force of gravity down is 245 newtons, then that means the normal force up must also be 245 newtons. Why? Because the problem doesn't indicate that we are experiencing up or down acceleration. The vertical forces then must be balanced. And so to finish this one off, how large is the force that you exert to keep this going? Well, it would be whatever the combination of those are. So let's go ahead and multiply it by 0.2. And it looks like the answer for us, if I don't skip ahead, is going to be 49 newtons for our applied force. So answer, you are pushing with 49 newtons to keep this thing going at a constant speed. All right, let's keep on going. A couple more examples. Jose pushes the lunchbox with a force of 5 newtons, and it moves at a constant speed. So what does that mean? Well, that means that the force of friction also has to be 5 newtons. So what's the magnitude of the force of friction? We could say force of friction equals 5 newtons. Well, that's a piece of cake. What's the coefficient of friction between the lunchbox and the table? Well, we know if you're going at a constant speed that the force of friction is equal to the applied force. We already kind of accounted for that. But the force of friction is going to be equal to mu Fn. All right, that's just the definition. And again, with the less than or equal to thing, I hope I've shown you by now, since we're setting this maximum force, since we know we're going at a constant speed and friction is doing its thing to the max, that's why we can go ahead and set this equal to each other. And so we'll plug this in. We know 5 newtons over here equals, it's asking us for the coefficient of friction, which we don't know. How about Fn? Well, we know Fn is straight up because Fg is straight down. And since we're on a flat surface and not experiencing vertical acceleration, we know that those two forces are equal. So similar argument holds as the last one. Fg equals mg. And since we're doing a math type problem here, we're going to go ahead and use the 9.8 to be nice and precise. 5 times 9.8, pretty sure that's, oops, sorry, wrong one. 5 times 9.8 is still going to be 49 newtons for us. All right, and if Fg down is 49 newtons, then Fn up must be 49 newtons. If you said that, you're right. And so this guy would go in here for 49 newtons. We would divide both sides by 49. And a nice little note here on the mu, the coefficient of friction, it's usually a decimal less than 1. Well, duh, because it's a decimal. But I mean, it usually has a value of less than 1. There are very rare instances, if you look up certain weird materials, where that violates that principle. But as a general principle, you should be getting a decimal answer for your coefficient of friction. So there, that one is 0.10. All right. Now, what about if you have acceleration? I want to get to this one before we end up for today. So the Sun Chips kid, it's a good old tale of Mr. Simpkins' days, pushes angrily with 8 newtons, and it says we'll use the same force of friction as the last time, so we'll say the force of friction is still equal to 5 newtons. It says what's the net horizontal force acting on the lunchbox. All right, so the net horizontal, 8 to the right, 5 to the left, it would be 3 newtons to the right would be our net horizontal force. And then at what rate does the lunchbox accelerate? Well, F equals ma, and we already did the net force is 3 newtons, so the mass of the lunchbox is 5 kilograms. And of course, the acceleration of this would be like that. So we'd solve for the acceleration by dividing both sides by 5 kilograms. 3 over 5 is the acceleration would be 0.6 meters per second squared. All right. So that is all I have for you for our friction introductions. You should also make sure that you checked out the College Board video of the day for contact forces for friction. And as you go forward into the asynchronous lesson for our next one, you guys are going to be doing a video analysis of a box sliding across the floor. So tune in to the next video here for week 8 asynchronous 1 for how to do the real world friction lab. Until next time, I'm Mr. Simpkins in the Simpkins Physics Corner.